In the last talk, we wrote down Newton's second law in terms of momentum. And that told us that the net force acting on an object is the time derivative of the momentum, where P, the momentum, is a vector quantity equal to mass times velocity. What I want to do here is rearrange this equation so that we obtain what's known as the impulse momentum theorem. I'll rewrite it in the way that our book gives it, which applies to the most common cases we'll encounter, and then we'll talk about it before we look at some examples and problems after this. Okay, so the first thing we want to do is to just rearrange this expression so that we obtain the first result we need. What I want to do is, as we did in the last talk, move this dt up here and integrate this equation. So what we end up with is dp equals the net force acting on the object times dt. And we're going to integrate both sides. The idea here now is that we have an object or a system or something that we're studying that has a force acting on it over some time. And we see that the effect of that is to change the momentum. This integral is going to tell us the accumulated effect of all these momentum changes. So if we have a force that gets exerted from time 0 to t, and the momentum goes from some initial value to some final value, what we get out of this, on the left we have change in momentum, delta p. That's just p final minus p initial. And on the right is the integral of the net force on the object times dt from 0 to t. Now what we really need to do here is rewrite this in the way that we'll use it most often in class, and then talk about it to get some insight. Let me give you a stereotypical problem that we'll encounter. They tend to go something like this. Suppose you have a golf tee, so here's a tee, and there's a golf ball resting on this thing, and somebody comes up and whacks it with a golf club. So there's the golf club that comes in, and they hit this thing, and the golf ball goes flying off at some velocity. So the problem might give us the mass of the golf ball, and it might tell us how long the club is in contact with the ball, and it might tell us what the final speed is, and we could be asked to find the force that the club exerted on the ball. Now the key thing here is that this sum of forces involves several forces. Weights acting on the ball, there's a normal force acting on the ball, and the club is hitting the ball with some force that we can call F. Most of the time, the change in the momentum that we're worried about comes from a single force. In this case, the ball's weight and its normal force are going to be negligible in considering the ball's motion compared to the force that the golf club exerts on it. That force is going to be massive. I'll draw it here as F, compared to the weight and the normal force. This force is going to dominate the motion during the time that the club is in contact with the ball. During that time, the force F is going to be way bigger than any other force. So we're going to make an approximation here that this net force is the dominant force. It's the force, in this case, of the club pushing on the ball, making it move. If we were to plot that force, maybe it looks something like this. So here's time, and here's the magnitude of that force. Now what happens is this club comes moving in, and for a while it's not in contact, and then it touches the ball. So we move along here with no force, and then the club touches the ball, and imagine we're watching this in slow motion. The club is going to compress the ball, and it squishes it a bit as the force gets bigger and bigger, and then the ball goes flying off. So the force gets less as the ball flies off of the club head. So here we are at an increasing force. The ball is getting smushed. It's a maximum, and then the ball goes flying off, and it loses contact with the club. So the force as a function of time might look something like this. So I'm going to rewrite this expression to say that the change in momentum is the integral of that force that the club exerts on the ball, integrated over time. And here I'm essentially ignoring all of the little forces. Weight's going to be small, normal force is going to be small. The thing that's going to dominate the motion of this golf ball is the force F that the club is exerting on it. Now, two things to do to this equation before we give it a name. First, I'm going to say that this equals J, which our book calls impulse. Okay, so what is the impulse? Well, it's the change in momentum, and it equals the integral of the force on an object over time. So you can consider the impulse to be this integral right here. The force acting for some time changes the momentum, and those things are what we call impulse. That should be a vector. All right, the other thing I want to do here is to re-express the right-hand side of this equation. This thing right here, the integral of the force dt, is telling me to find the area under the force time curve. That integral, at least the magnitude of the f there, tells me to find this area that I'm shading in. And in general, it's a complicated integral to do. As the club hits the ball, the force is going to go up, it's going to take some weird shape, and it's going to come back down. Not an easy integral to do. The way we often write this is to say, let me re-express this as the average force exerted on the ball times delta t. And what do we mean by average? What we mean by average is I want to find a constant function that gives me the same area under the curve as that integral did. So let me draw it here in red. Suppose we replaced this blue force varying across time with a constant force that started right here and ended right here, so that we call this delta t. Okay, then we can say that this is the average force, F average, if this red area equaled the blue area. And that is what this equation down here is telling us. This is the area under the curve, this blue curve, and this right here is the area shaded in red under the rectangle. And we want those two things to be equal. The area under the rectangle is its height, average force, times its width, delta t. So this gives us our definition of average. What do we mean by average? What we mean, looking at this equation, is the average is the integral of some function dt divided by the integral of that thing that we're integrating over, dt in this case. So the denominator becomes delta t, which is this delta t, and the numerator is the integral over that same quantity. This equation is the impulse momentum theorem. I'll put it in a box right here. This guy is the impulse momentum theorem. And it tells us there's a thing called the impulse. It equals the change in momentum, and it's the integral of the force over time. Most often, we're interested in the average force times a delta t. Let me erase some of this, and we'll talk a little bit more about it. All right, so I'm going to move my impulse momentum theorem up here out of the way. And we'll give it a name. This is the impulse momentum theorem. I'm going to write it in a more compact way. The impulse, J, is synonymous with the change in momentum, delta P. And remember that momentum is a vector, so its magnitude can change and or its direction can change. Most often, we will write this as the average force times delta T. Now, what do we do with this equation? A common application is to solve this for the average force. if I wanted to know the average force on this golf ball, what I would do is I would say the average force from the impulse momentum theorem is the change in momentum divided by however much time that club was in contact with the ball. So I could write this as the ball's mass times its final velocity minus the ball's mass times its initial velocity divided by delta t. And writing it this way shows that this is really just a restatement of Newton's second law. The force is the change in momentum over change in time. And we've now averaged this over some time that a force is in contact with an object or a system changing its momentum. Before we leave this and look at some more examples and problems, I just want to do one quick calculation to point out the most common error students make in using this equation to help you avoid it. Let's consider this. Suppose we have a tennis ball, looks like this, and it's going this way at 20 meters per second. And then somebody's going to hit this tennis ball with a racket. So here's a tennis racket, right? And they're going to swing this racket like this so that the ball hits it and it gets shot back out the other way. So here comes the ball after being hit by the racket, and it's going to go this way at 30 meters per second. Imagine we had filmed this person hitting the tennis ball in slow motion, and we found that delta t, the time that the racket is in contact with the ball, turned out to be 1 millisecond. And let's say that the tennis ball's mass is 0.05 kilograms. All right, and the question says, find the average force that the tennis racket exerted on the ball. So find F average. As usual, we'll take our x direction to be this way. Now we're going to do this using the impulse momentum theorem. The average force that the racket exerts on the ball can be found with this expression. Here it is, the average force, and it's the change in momentum over change in time. We'll put the numbers into this expression here. So what is the average force? Let's write it out. Average force equals, I'm going to factor a mass out of this expression. This is the tennis ball's mass times Vf minus Vi divided by delta t. Okay, let's see what numbers we end up with here. The tennis ball's mass is 0.05 kilograms. And now I need to multiply by Vf minus Vi. Notice that both of those vectors are in the x direction. So I'm going to factor that direction out over here and have an I hat. And what I want inside are the components. The first velocity that we have to deal with is the final velocity. That's this one right here. After the ball has been hit by the racket, the final velocity is 30 meters per second in the positive x direction. So Vf is 30 meters per second. And then we're going to subtract the initial x component of velocity. And this is where the easy mistake happens. We have to take into account the direction that this thing is going in. These are vectors, so direction matters. Before the ball is hit by the racket, it's moving to the left in the negative x direction. So the x component of the initial velocity is minus 20 meters per second. So we're going to subtract off minus 20 meters per second. Watch for those negative signs. Momentum is a vector. Direction matters. And we'll divide this by the time that the ball is in contact with the racket, and that's 1 millisecond. 1 times 10 to the minus 3 seconds. We can probably calculate this in our head without calculators. This is a difference of 50 meters per second. The ball was going this way at 20, it came out at 30, so the change in the velocity was 50 meters per second. Watch for that. That comes from the direction. 50 meters per second times 0.05 kilograms gives us a momentum change of 2.5 kilogram meter per second. And we divide that by the contact time, 1 millisecond. So we end up with 2.5 times 10 to the third kilogram meter per second squared, which is a newton. 2.5 kilonewtons of force, on average, that the racket exerted on the ball to turn its momentum around from going this way to going this way, getting a little longer in the process. All right, so as you're solving problems, watch out for that. Make sure you keep a close eye on directions and the negative signs that can come along with them. Now, I'm looking over this, and I just spotted another very easy mistake to make. I wonder if you noticed it also. An advantage that I have is that I've made all of these mistakes hundreds of times each, so I've had a lot of practice finding them. Here it is. When I'm looking over this, I notice this is a vector. It's a force, vector, magnitude and direction. So this is a vector. And suddenly it equals scalars. What happened here is I made the classic mistake of starting out writing a vector equation. Along the way, I dropped the direction information. So all I have are scalars here. And vectors cannot equal scalars. This is not the worst mistake to make in the world, but it is one that we should fix. We'll go back and do it in a minute. It's sort of equivalent if you were writing an English paper of dropping the period at the end of your sentence or the question mark at the end of your sentence. It's necessary. It carries necessary information, and we should have it there, but it's easy to forget sometimes. So let me back this off, and here's what I need to do. I need to keep my I-hat right there. And then I can write this as 2.5 times 10 to the third newtons in the I-hat direction. So I have a force of 2.5 kilonewtons, and this tells me that it's going in the positive x direction. The force of the racket on the ball was this way. That's the direction that the force was in. All right. I'll stop again, and we'll move on to some examples.